Okay, so we're going to start off with a sweeping review of one of the first things that we studied, if I can remember to unfreeze the board. That thing is kinematics. Primarily, we're going to start off and focus on some of the important things to remember here in one-dimensional kinematics, and then I'll have a second video that deals with projectile motion, which is more broadly two-dimensional or three-dimensional sometimes kinematics, although for the most part all you'll be dealing with is two-dimensional. So a list of some of the useful equations, and these will carry over to projectile motion as well. Now, I provided you with a chart in class. If you can, it's not necessarily a bad idea to be familiar with all the equations on that chart because it makes it far more versatile. However, the key ones to take a look at, if I had to choose a few to know, the very first one is definitely going to be this. Delta x equals v naught times t plus 1/2 a t squared. This is one of the most useful ones. This, out of the variables that I provided you for the chart, this is the one without the final velocity. These are the common types of variables that you end up with on problems dealing with kinematics. Two of the others that are very useful are ones that let us use the final velocity. One of the ones I like to have on hand is final velocity squared equals initial velocity squared plus 2 acceleration times delta x. So in other words, our acceleration times our displacement. And then the other one is v final equals v initial plus acceleration times time. Now technically, if you're familiar with these three equations, you should be able to derive the other two just by solving one thing in terms of another. You could find your initial velocity here, for instance, and plug it in up here. You'll find that it simplifies down to the equation that has everything except for the initial velocity. And so that's one example where if you've got three of them, you can derive the others, although deriving takes some time. So, most important, I'd say, is be familiar with that, be able to use that at the drop of a hat, and being able to use these are also very good. Now, one of the others that is listed is that delta x equals v final plus v initial divided by 2t. The main reason that I bring this up is one of the things that you want to be very careful of. I've seen many students do this recently, where they say that, let me phrase this a bit differently, that your velocity equals your displacement divided by your time. This is not always true. Be careful relying on that. That is only true when you have zero acceleration, I believe. I'd have to double check, but yes. In fact, we can see it up here in this equation. When my acceleration is 0, this term goes away and I have delta x equals my velocity times time. When you have acceleration, that's going to change. You want to be very careful accepting that one. The one that's kind of in its place is one of the other kinematic equations, which is this guy. What this actually has you find is your average velocity. So if your velocity is changing over time, your average velocity is going to be, well, the average of those. It will be neither your initial velocity, nor will it be your final velocity. It'll usually be the average of those two, so we add them together and we divide it by 2. We can see this equation is one of our kinematic ones, and it's much more reliable. So be very careful relying on this. You can use that if you've got zero acceleration, but if you remember this equation like I recommended for you to do, then you've already got that down. All right, so some of the other things to keep in mind. These equations, and I cannot stress this enough, these equations only hold when acceleration is constant. At some point, I will go through and I will make a set of videos that show where these equations come from. They come from the calculus side, and you have to make the assumption that the acceleration is constant. Now, most of the problems we deal with, at least that we actually solve, we have constant acceleration, so it's okay to use these. But you must be careful of that. There are many conceptual questions that I ask and other people ask where I'll set up a circumstance where your acceleration is not constant, and then I will ask you something about these kinematic equations. We can't answer it. When the acceleration is not constant, these kinematic equations are no longer valid. The final thing that I'll mention on this is the way that I've got this set up. Each of these equations, well, even independent of the way that I've got them set up, are for a single dimension or direction. In other words, you only operate in the x direction. or you only operate in the y direction. Be very careful. We're going to take a look at how this expands into two-dimensional motion soon. But one of the main things that a lot of people make mistakes on is they'll use the displacement in the x direction and an initial velocity in the y direction. All of these, especially for the very first step here in kinematics, this is all for one direction. So, originally I thought about going through and solving a few sample problems on this, but what I'm going to do with these review sessions is I'm going to hopefully include a link here at the end to related videos that we've already had from homework-related stuff. So, but this should be most of the kind of important concepts to deal with kinematics. Big things are these handful of equations you'll see in projectile motion, that if you've got these equations, you've already actually got all the equations you need for projectile motion. Big thing is acceleration is constant.